Hello and welcome to the second day of Conics, Chapter 9a. I wanted to first give a thank you to Mrs. Manton for typing up these notes and creating these wonderful set of problems. It is a great help to me, especially while I'm gone this week, and hopefully to all of you. So let's get started. This is about circles. I know you know what a circle is, but let's start labeling the important parts of a circle. A circle has a center. On an XY ordered plane or coordinate plane, that is an ordered pair. Right now I'll just put a little C there for center. We know that circles have a distance from the center to any point on the circle. We call that a radius, which usually carries the abbreviation of the letter or the variable r. We have twice the radius, which I draw a line segment that goes through the radius, whose endpoints are on the circle. That is called a diameter. Usually use a lowercase d. A diameter splits the circle into two semicircles. And finally, and let's see if I can use a line tool for this. Let's pick a different color. Finally, we have the line that touches a circle at exactly one point. I'll do my best on this one. This likes to click into grid behind. There we go. Okay, that's okay. A line that touches a circle at exactly one point is called a tangent line. Let's use singular. So these definitions are here on the left. To circle all points that are the same distance or equidistant from a given point in a plane called the center. The radius, line segment whose endpoints are the center and a point on the circle. Diameter, segment whose endpoints are on the circle and passes through the center. The diameter is equal to 2 times the radius. And finally, a tangent line, a line in the plane of a circle that intersects the circle in exactly one point. This is important, last little thing. I would take out a highlighter and highlight this. The radius is perpendicular to the tangent line at the point of tangency. If I look and zoom in on this circle right here, and let me kind of clear this diameter, let's just look at the point of tangency. If I were to draw a line segment from the point of tangency to the center of the circle, this is now a radius, but this also creates a 90-degree angle between that particular radius and the tangent line. This point right here is called the point. This point is called the point of tangency. So those are some labelings for you. Now let's kind of get back to the math of this. We have this standard form of the equation of a circle. And this is a neat derivation because it uses the distance formula that we did yesterday. If you think about it, if we want to take and hold this distance constant, this radius, we know that we have this distance we're going to call radius. We know that the center, if we give the center coordinates, I'm going to erase the diameter, but if we give the center coordinates of x or h comma k, which is the standard used when describing the center of a circle, the vertex of a parabola, and other points of importance. Now I'm going to erase the tangent line, and I'm going to erase the perpendicular mark, and let's talk about this radius. If that circle has a point x comma y, and that point is a variable point that could represent any point on the circle, and the center has coordinates of hk that are fixed, that cannot change, I know that the radius is equal to the distance between the variable point and the center. And this is just using a distance formula between those 2 points. Now instead of d equals, I'm using radius equals. But if I took this formula and squared both sides, I would actually have the standard form for the equation of a circle. R squared is equal to x minus h squared plus y minus k squared, where hk is the center and the radius is r. Now, this particular equation of a circle resembles another equation that we know as well. That would be c squared is equal to a squared plus b squared. Because if you pick a particular point, you're talking about a distance to that point, and that distance is another application of the Pythagorean theorem. So all of this relates. This is all kind of related to the Pythagorean theorem. And it's important that you see that connection so you can help understand and remember this equation of a circle. In addition to the distance and the midpoint formulas, this is another formula that you must memorize. If you cannot derive it, you must absolutely memorize this. You will use this quite a bit in the next several years. So the first set of directions say to write the equation of a circle, given the center and the radius. I have a center at negative 12, 3 and a radius at 2 radical 5. If we do just a simple plug and chug, I know that h is equal to negative 12, k is equal to 3, r is equal to 2 radical 5, and I'm going to plug this into the formula. Pretty easy. 2 radical 5 squared is equal to x minus a negative 12 squared plus y minus 3 squared. Well, let's clean this up just a tad. 2 radical 5 squared is 4 times 5, or 20, is equal to x plus 12 squared plus y minus 3 squared. For the next problem, the center is negative 9, and radius is 1/2. Really, we're just going to go directly to the equation. I'm going to start with x minus 8 squared plus y minus a negative 9 squared, or y plus 9 squared, is equal to, and 1/2 squared is 1/4. Like before, we're going to keep as much of this in fractions and simplified radical form as possible. No decimals. Next set of directions say if the graph of the given equation is a circle, find its center and radius. If the equation has no graph, say so. Let's kind of look at that last part. I mean, if we put that in there, there's probably going to be something that has no graph. Alright, let's go back to number 3. So this is the graph of a circle, but we have a problem. It's not in graphing form. And again, I'm going to write graphing form just up here. We want to compare it to graphing form in order to get it there. This means we're going to have to complete the square twice. So what I do, and what I recommend you do, is look at your x terms and look at your y terms. And we're going to group those together. I'm going to go x squared plus 14x plus, and like before, I'm going to put a box. But then I'm going to switch colors, and you don't have to switch colors, and go y squared plus 2y plus, and I'm going to use a hexagon because I like the shape and it's big enough to write something in. Equals, I have negative 40 plus, and I still have that box from before. Whatever I add to the left, I must add to the right. And I also have plus a hexagon. That's a bad hexagon, but you get the idea. Now we just kind of have to fill in the box in the hexagon. Moving that over, half of 14 is 7, 7 squared is 49. So 49 goes in the box. Half of 2 is 1, 1 squared is 1, so 1 goes in the hexagon. And you get, when we factor the x's and we factor the y's, we get x plus 7 squared plus y plus 1 squared equals, and you have 49, negative 4, that would be 10. So I know that my center has coordinates of negative 7, negative 9, opposite sign for h and k, and I know that the radius is the square root of 10. Not 10, but the square root of 10. So that's the center and radius, and really, when you think about it, the circle equation is just another way to report that information, albeit a little bit more mathematically. Let's try this one more time. Actually, we recommend you pause the video, try this one on your own, flip through it, and when you get back, see if you're right. Okay, we're going to group the x squareds and the minus the 2x. I'm going to put that plus a box, and I'm going to stick that in parentheses. Then I'm going to go plus y squared plus 2y, then plus a hexagon equals, let's move the 8 over, negative 8 plus a box plus a hexagon. Going inside the box is a 1. Going inside the hexagon is also a 1. And you get x minus 1 squared plus y plus 1 squared equals negative 6. And we have a problem because we have the sum of two squares equal to a negative number. If I try to figure out what is my radius, I get radius is equal to the square root of negative 6. That is not possible. Radius is a distance. It's not an imaginary or complex number. What this means is this graph is not a circle. In fact, it is not anything in the real number plane, so don't worry about it, other than saying it's not a circle. If you have to give a reason, it is not a circle because r squared is negative, which just doesn't make sense. Also doesn't make sense if it's 0, because that's just a point. Okay, let's go to the next one. Completing square on this, I'm all about looking at optimal methods for you to do, and I immediately noticed that we have a lot of even numbers. So let's take a step and divide both sides by 2. X squared plus y squared minus 10x plus 8y plus 16 is equal to 0. Group the x terms together, add a box, then group the y terms together, add a hexagon, equals negative 16 plus a box plus a hexagon. Always seem to run out of space on the right. So then half of 10 squared is 25, half of 8 squared is 16. Then I've got a 25 that I can barely write in that box unless I zoom in. And 16. Okay, factor. We get x minus 5 squared plus y plus 4 squared equals 25. Center, positive 5, negative 4. Remember, opposite signs. And radius is square root of 25 is 5. Last one in this set. If I look at these, I see that I can't factor, or I can't divide both sides by a common factor, but I do need to get the x squared and the y squared to be positive coefficient, or sorry, to have a coefficient of 1 if I'm actually going to complete the square. So we got two sides of the equation. We know that they're both the same coefficient, and keep in mind that that was actually important, that both x squared and y squared were the same coefficient. Otherwise, we wouldn't be able to do what we're about to do. And I'm just going to divide both sides by 9. X squared plus y squared minus 2/3 x plus 4y plus 4/9 equals 0. So now we've got to complete the square on the x and the y and move the 4/9 over. X squared minus 2/3 x plus a box plus y squared plus 4y plus a hexagon equals negative 4/9. Well, then we have half of 2/3 squared. Half of 2/3 is 1/3. 1/3 squared is 1/9. Half of 4 squared is 4. Then plus that box, which is 1/9, and plus that hexagon, which is 4. So then we have x minus 1/3 quantity squared plus y plus 2 squared equals, so we have negative 4/9 plus 1/9. Negative 4/9 plus 1/9 is negative 1/3. Negative 1/3 plus 4, which is 12/3, is 11/3. My center is 1/3, comma, negative 2. And the radius is equal to the square root of 11/3, which when we rationalize with radical 3 over radical 3 equals radical 33 over 3. Number 7, we're going to do the same thing, but now we're going to graph it. If your graph is ridiculously off the coordinate system, you are probably doing something wrong. X squared plus 8x plus a box plus y squared minus 6y plus a hexagon equals nothing to add over, so it just equals box plus hexagon. 16 and 16, 9 and 9, and we get x plus 4 squared plus y minus 3 squared equals 25. This means a center is at -4, +3, and radius is equal to 5. So when we graph a circle, we're going to plot the center, -4, +3, and with a radius of 5, really there are only 4 points that we can graph safely. And those would be our up, down, left, right points. I've also heard them called the north, south, east, west points. Positive x, negative x, positive y, negative y, whatever you want to call it. We're just going 4 directions, 4 cardinal directions. Up 5, down 5, right 5, and left 5. If you have a compass, awesome. Really not used that much anymore. Funny story to tell you about that later. But if I wanted to start and do this and kind of arc it well, I just kind of do my 4 arcs separately. I need to do one. Then I'll do one here. If I don't like one, I can always erase it. Try again. I'm not going to be too perfectionist on this. If you do a Google search for perfect circle or perfect person drawing a perfect circle, you will find a college professor who can draw a perfect circle. Mine always tend to look a little bit diamondish, but there you go. That's a representation. Okay, let's look at some other application problems we can do. We have a circle that has a center at 4, -2, and passes through 5, 3. Underneath I'm going to kind of sketch. I see that this is an HK, and 5, -3, that is one possible, and I'm going to emphasize that it's one possible XY. It's not the only XY, but it's one possible XY. Remember, XY are variable points. There are infinitely many points on the circle. But HK is a fixed point. There's only one HK. And we're trying to plug this in here and get our missing information. We aren't missing X and Y. We want to keep it X and Y. We aren't missing H and K. We are missing our radius. So the best way to do this is actually just to plug it in and not get the radius, but just get R squared. We only want to know what R squared is. Yeah, we could do a distance formula on these 2 points and get the radius that way. But that's kind of shuffling around formulas a bit too much, and I think it's just easier to say 5 minus 4 squared plus 3 minus a -2 squared, or 3 plus 2 squared, equals R squared. So I get 5 minus 4 squared is 1, plus, that'd be 5 squared is 25, equals R squared, or 26 is equal to R squared. Then I'm going to take that R squared and plug it back into the original graphing form. Then I'm going to take the HK, plug that into the graphing form as well, and keep XY as XY, leaving my final graphing form as X minus 4 squared plus Y minus -2 squared equals, and we know R squared is 26. We have this problem type called endpoints of a diameter. This may be helpful to graph on graph paper if you need to see it, or maybe just is kind of early and you want to see it. I'm going to do a little sketch of a circle using a circle tool, and maybe plot a diameter as best I can. Again, this program likes to click into an invisible grid behind this page, so it's really hard to just kind of plot stuff. I'm just going to draw it by hand. That's not bad. There's a center, and we're going to say the endpoints of the diameter are these 2 points. Maybe this is -4, 3, and this is 12, 9. Again, this is not drawn to scale or anything, but we need to know 2 things to get the equation of the circle. So I need to know the center of the circle, and I need to know the radius. I don't know either of them right now, but I have enough information to get both. Well, we know that the center is the midpoint of the diameter. And if I have the endpoints of a diameter, remember there are infinitely many diameters you can do, but if I have the endpoints of one of them, I should be able to figure out what the center of the circle is. Let's do that right now. Let's try this method of listing, one of my favorite methods to find a midpoint. 12, 9 and -4, 3. Kind of finding this midpoint in here, so let's look at the 12 and -4. Average them up. 12 plus -4 divided by 2 is +4. Quick check, -4 to 4 is 8, and 4 to 12 is 8, so that's in the middle. And 9 and 3, I think you can look at that and say safely that that's 6. So there's our midpoint. Now we need a radius. Well, we have a midpoint. Now this just becomes like the problem we did before. Let's go back to the equation of the circle. If I were to plug what we know in right now, I would get x minus 4 squared plus y minus 6 squared is equal to r squared. If only I knew one of the xy points. Oh wait, I know two of them. Let's just pick one of them. Let's pick this one because those are positive big numbers. This might be a little easier. I'm going to take that and plug it into x, plug it into y, and solve for r. 12 minus 4 squared plus 9 minus 6 squared equals r squared. I get 8 squared, which is 64. 3 squared, which is 9, equals r squared. And I get r squared is equal to 73. Great. Well, I don't really care what r is. I want to know what r squared is because that's what I need in the equation. So let's take these two circle pieces of information and build our equation. X minus 4 squared plus y minus 6 squared is equal to 73. I'd like to take a moment right now to show this on your graphing calculator. If you go to a graph in your graphing calculator and you see you have an empty graph here, if I hit the menu button and I go to graph entry edit, that's the third option, and then I go to equation, I see that I have an option to enter a circle. If I hit that, you see two forms for a circle. The second form is the one you use if you haven't completed the square, and the first form is the one you can use if you have completed a square. So I complete the square, and I can just type in x minus 4, and then y minus 6, putting the last problem in, equals, and instead of, well, it wants us to put radius in. If we're going to actually do this, we should put in radical 73, so that radical 73 squared is 73. Press enter, and you can see we have a circle centered at 4, 6 with a fairly large radius. If I kind of move this up, you can see that the circle is a fairly large radius. So you can graph this on your calculator and just kind of see what it looks like. It's not really a huge advantage to it, but it's something you can do. If you did not have these menu options and you're wondering what the heck I'm talking about, that's because this feature was added this past summer in the graphing calculator operating system. All of your calculators can be updated to see this, so if you would like that, just come and see Mr. Elliott. It takes about 2 minutes to do, not longer than that at all. Let's go to number 10. Find the equation of the circle with center at -1, 4 and tangent to the line x equals 3. Well, we don't have graph paper here, but I always find it helpful to draw a little sketch. I'm a visual learner, and I'm going to put a plot at -1, +4. So circle is at -1, +4. And tangent to the line x equals 3. So 1, 2, 3. X equals 3 is a vertical line here. Okay, one more calculator thing. Since I'm a calculator buff, if you go to this equation and go to line, we can actually do x equals 3 as a line. I know you know what a vertical line is, but this may be helpful later on when you do your check of yourself. You can actually check with your graphing calculator to see that your answer is correct. So we have a vertical line at x equals 3. Its tangent to that line, center is at -1, 4. Now, if I take a line from that center and draw it out to this tangent line in a direct way, the shortest possible distance between them, so that it's perpendicular, I know right now I have a radius. I know that because a point or a line segment drawn from the center of a circle to a point of tangency is perpendicular, and it is a radius. I know right now that my radius is 1, 2, 3, 4, 4 units. Radius is 4. I also know that my center, my HK, is given. I'm done. I have my circle. I can go directly to the equation. X minus a -1 squared plus y minus 4 squared equals 4 squared, which is 16. Now you can celebrate and kind of sketch your circle if you want. This is what the circle would look like, albeit a little crudely. If I want to do a little bit better, I'd go down 4, up 4, left 4, and try to make a better example of a circle that works. But in the end, that's what the circle would look like. Number 11, last one, graph each semicircle. Since it's a y-equals, this is going to be a function. It's not going to be a full circle, because a full circle would fail a vertical line test. Two ways to do this. One way, the default way, and I'm emphasizing this because if you're ever stuck in how to graph, you can always graph by t-chart. If I took this and factored what was inside to kind of get an analysis of what's going on, I'd have x and 8 minus x. And I should know enough to know that I would have two x-intercepts. One would be at 0, 0, and the other one would be at 8, 0. So if I graph that 0, 0, and 8, 0, 1, 2, 3, 4. Now, it's possible that my circle could go like this or like anything else. That at least gets me a start. Then I can start looking to see, is there anything that I can plug in that would make this be perfect square? Well, halfway between 0, 0, and 8, 0, we have 4, and if I plug in 4, I get 4 times 4, square root of 4 times 4, I get 4, 4. So I go there, go over, and go up 4, and suddenly I have something that looks, the circle can only go one way with this. Why can only go one way? Well, if I connect it like this, now we see that this is really forming a good arc. So that's kind of looking left to right and seeing, what are my possibilities to graph, just graphing by t-chart. Something else to keep in mind, if I look at this and I think about my domain, I know that x cannot be negative, and if I do a sign graph really quick with my two roots, my critical values of 0 and 8, I could have closed circles on either of them, and the values that I could only use, if I tested like a positive 4, I would get a positive number, which is good because I can only have positive numbers. Remember that this whole radicand has to be greater than 0. My domain would have to be restricted between 0 and 8. Now that's using a sign graph to kind of take a look at the fact that basically 8x minus x squared has to be greater than or equal to 0. So the only values I could really test would be in between 0 and 8. Everything else wouldn't be there. Second way to do this, if that's completely confusing you, is actually to square both sides. We get y squared is equal to 8x minus x squared. Now whenever you square both sides, you run the risk of having what we call extraneous roots. But if you square both sides and then complete the square, I'd have x squared minus 8x plus 16 equals, or plus y squared equals 16. Y squared is already factored, it's already completed, it's just x minus 4 squared plus, and we can think of that as y minus 0 squared is equal to 4. Now that is a circle. It's a circle centered at 4, 0 where we see this center, but it's the positive part of the circle because if I go back up here, there's actually a positive square root. If I wanted to make it the bottom circle, I'd have to do a negative right there. So, knowing the center of the circle and the fact that the radius was negative 4, sorry, that should be 16 right here, 4 squared. Knowing that the radius is equal to 4 would also get me this same semicircle. Okay, this is your homework, and good luck.